We're going to spend most of our time on this lecture looking at phase changes. And this is probably something that you talked about sometime last year in regular chem. So first thing we're going to do is create a little graph and just put some very simple labels on here. And G, increasing going this way, and temp over here on the Y. And put just kind of a generalized progression here as we add in energy. Temperature kind of goes up and it levels off and then it goes up again. We're going to use water as an example. And in this area here, because it's really cold, call it a solid. In this stage here, the solid is melting, so solid to liquid. Got a liquid going on here, and then our liquid is vaporizing here, turning into a gas, and then this is simply the gas. So again, we're going to stick with water in this understanding, and therefore we have some very specific values that go along with it. When you are heating the solid, it takes about that much energy per gram per degree Kelvin to raise the temperature 1 Kelvin. When you are melting that solid, it takes a very specific amount of energy, 6.01 kilojoules. Notice this is a much larger value because kilo is 1,000. That much energy per mole. Now notice the difference here. We're going through the heat of vaporization. We're talking about moles, and we're talking about heating the solid, we're talking about grams. Don't ask me why. This is kind of a standard that people typically use. If you are going to heat up the liquid after it is all melted, 4.18, many times it's 4 joules per gram per Kelvin or degrees Celsius, it works the same. And then when you are vaporizing that liquid, 40.7 kilojoules, which is a pretty big number comparatively to everything else we've seen on here, per mole. And then lastly, the one up here at the top, when you're just heating up the gas, 1.84 joules per gram per Kelvin. So those are all little parts in here, and a really terrible problem would be is if you had a solid, whatever many grams, sitting somewhere down at this temperature, call it -10. You would have to go through 5 different equations to get a final answer. Let me give you some equations that kind of go along with this. So for example, if I'm dealing with this equation up here, I would have Q is equal to mass. I got a pretty tight area here, so I gotta squeeze this in. Mass times change in temp times Cp for the gas. If I'm in this range right here, I'm looking at a heat of vaporization, the enthalpy of vaporization, whoops, that's a V, times the number of moles of that material that I have. If I'm in this area right here where I'm heating up the liquid, that is a mass times a change in temp times the specific heat value for the liquid. And then in this range right here, again, the energy, heat of fusion, F, times the moles. And then lastly, the mass times the change in temp times the solid. So these are the 5 different equations we may use depending upon what initial temperature we start with and where it wants us to take it to. Don't forget in this area here, if we're specifically talking about water, this is going to be 0 degrees Celsius, and this will be 100 degrees Celsius. And we can change it over to Kelvins if you'd like to. All right, let's do a homework problem and see how that shapes up. We're looking at number 45. And for this particular problem, we have ethanol, and it melts at this temperature, and it boils at this temp. We have a heat of fusion value of this, and we have a heat of vaporization, enthalpy of vaporization, of this. Specific heats of the solid and the liquid are these two values there. So tons of information. Wow, there's a lot there. We are trying to figure out how much heat energy is required to convert this mass of ethanol from this temperature to the actual vapor stage. So we're going to vaporize at this very specific temperature, and that has to be the same number. So we have to start at this temperature, and understand again, so it melts at this temperature, so we are within the liquid state. So we have to be within liquid state and heat it up. So we have two different formulas we're going to be working with. We're going to work with Q, the mass, and we're kind of generalizing this off of the graph we just used in the previous problems, times the change in temperature and the specific heat value when heating a liquid, based on the starting temperature up to this temperature here. The other equation is simply the vaporization. So the enthalpy value for vaporization times the number of moles that we have. So let's start with the heating up the liquid. So for that, we can deal with the mass. It tells us 42 grams times the temperature change that we have. So we're going from 35 up to 78. That happens to be 43 degrees Celsius or Kelvin. It works exactly the same way. I don't know why I put the brackets on there. Times 2.3 joules, and again, I'm getting that from right here, heat of vaporization, joules per gram per Kelvin. And that gives me an answer value of 4.15 kilojoules. It's a large number, and I just actually did the switch right here. The other problem is using that same 42 grams, but I have to be in moles. So I'm just going to add this step in here right now. Grams goes to the bottom, so I started with it. Go into moles, it's always 1 mole. If I do the molar mass of ethanol, it just so happens to be 46 grams. Once I have that, I can deal with the heat of vaporization, which is sitting right, where is that at? Right here. So I'll put that in here. It's per mole. So I'm just taking the moles and put it down here. I got a little more going on than that, but I will put it here. It's 38.56 kilojoules per 1 mole. And if I do this math, I end up with 35.21 kilojoules. And I want the total amount of energy, how much heat is required to go through the entire process. So I have to add those two guys together, and I get 39.3 kilojoules. That's the total amount of energy. So that's it. All right, for part B, I'm not going to run through because there's just too many steps involved. But I will tell you, if you go through it on your own, the answer you should come up with is about, ballpark, 60 kilojoules. And that would be it for that one. Okay, we got a little bit more to go through, and I think I will hold off on that one and do that in the next video.